the inclined plane. So what's going on? We could solve this using energy considerations, right? We have a potential energy due to a change in height turned into kinetic energy. We could even use that to find the final velocity and then find the acceleration on the way down, knowing the length. However, we could solve it directly. What causes this? It's the interaction of the force of gravity pulling straight down, but it doesn't accelerate straight down because there's also a normal force pushing perpendicular to the surface. And so I look at this and I'm like, what if I want to know the acceleration and I have forces? It's dynamics. So I know what to do. First thing, I panic. There's no formula for this. I'm going to have to think it through. The one thing I know is that the vector sum of the forces is equal to mass times acceleration. Okay, now I've got my forces. I could add friction. I could say there's a rope pulling in that direction. Let's keep it simple. A frictionless inclined plane. I only have two forces. And I ask myself that very important question now. Am I in equilibrium? I know I'm not. I saw it accelerate downward. So it's accelerating. And then you say, well, what is the direction of the acceleration? Why? Because I know the direction of the acceleration has to be in the same direction as the sum of the forces. And so I go in and I say, yeah, I know I saw it accelerate. It accelerates down the slope in this direction. And so now I'm ready to graphically add these vectors. I can say the force of gravity straight down plus the normal force perpendicular to the surface are the two forces, and they have to add to the sum of the forces. And so when I add these two vectors, they have to add to the sum of the force. Oh, wait, they have to be in the same direction, though. The sum of the forces must go in this direction, and so I can see this has to be the direction of the sum of the forces. And so I made the normal force way too big. Now I've got the normal force and the force of gravity. They're the sum of the forces. And the vector sum of the forces is in the same direction as the acceleration. And so now I can say, right, the acceleration is equal to the vector sum of the forces divided by the mass. Or the vector sum of the forces, this thing, divided by the mass. And I know that this is mg, the force of gravity. And so I can see for sure that the acceleration is going to be less than gravity because this force is considerably less than the force of gravity. And so very likely if this is frictionless, from this drawing I can see this is about half of what that is. So it's going to accelerate at about half of gravitational acceleration. Let's be a little more quantitative now. What do we know about these angles? Is this a right angle like it looks like it is? Well, I don't know. This is a direction of acceleration down the slope. This is a direction of the surface normal. This is normal to the slope, so yes, that's a right angle. And now how about these two angles? Is this angle theta down here or is this angle theta up here? Let's check. We could draw a triangle like this, and we see that this angle here is the complement of that angle. And so therefore this angle here is equal to this angle. And they're both complementary to that. And so we've got two right angles, two angles that are congruent. These two angles must be congruent. And I can check that. As this goes to 0, this goes vertical. And yes, both of these angles go to 0. I like it. How about the normal force? What do we see? As this goes to 0, we're in equilibrium in this direction, and the normal force and the force of gravity would be equal and opposite if we were not accelerating. As this gets bigger and bigger, the force of gravity would become more and more parallel to the slope, or the vector sum of the forces. And we would see this get higher and higher, and that normal force would be less and less. As you experience, does this make sense? As you experience, if you're on a slope and it gets to vertical, you're going to accelerate close to gravity, and you're going to find very little force pushing on you from that wall. Let me show you another way to look at this and another way to solve it. with a caveat that if you do it wrong, you're going to have big problems. Okay? So let's take a look at how to do it right. Just like we can add two forces to get a resultant force, we can take a force and break it up into its components. And so what I would do is I'd say, look, let's call this my new x direction and this my new y direction. And now I can break this up into the force of gravity perpendicular to the surface. Let's call that force of gravity perp. And the force of gravity in the x direction, or force of gravity parallel. Prove to yourself that this angle is the same as theta using this triangle, this right triangle, and this right triangle here. And then what I can see for sure is that this parallel component
is what causes the acceleration in the parallel direction.
I can break this gravitational force up to a parallel component in the x direction and a perpendicular component. These two are equal and opposite if there's no acceleration in this direction. And this component provides the acceleration. Now, this is a mistake students make. They break this up incorrectly. They say, oh, yeah, let's break up the force of gravity into this horizontal component and this perpendicular component. Okay, now there are a couple problems. One is these are not perpendicular axes, so this force has a component in this direction. But it's true. This force of gravity perpendicular plus this horizontal force does give you the force of gravity. Why is there a problem? Okay, one, this is now the hypotenuse, and this perpendicular component is greater than the normal force. And this force, if we're going to use this for the acceleration, we'd have to be accelerating in that direction. And that's not what we're doing. So this is wrong for this scenario. However, for another scenario, what if the acceleration were in that direction on this inclined plane? How could that be? That could be if the whole inclined plane were accelerating, which could be for an accelerating inclined plane. Or it could be for the situation with the fuzzy dice hanging from the mirror as we take off in our sports car. And in this case, you don't have a normal force and the force of gravity. You have the tension in the string and the force of gravity pulling on your fuzzy dice hanging from your rearview mirror. And then you add that tension and you add that force of gravity and you say, wait, my dice aren't accelerating downward. They're accelerating with my car in this direction. So then you'd have the tension plus the force of gravity gives you your vector sum of the forces, which is equal to mass times acceleration and must be accelerating in that same direction. So this is not the correct way to break up a force vector into its perpendicular components because these are not perpendicular components. So let's make sure we always do this right. And make sure that when we decompose a force, we do it in terms of components that are perpendicular to each other. So what do we take away from this? We make sure we put our forces in correctly. We ask ourselves that important question, are we accelerating? If so, what is the direction of the acceleration? If not, we know the sum of the forces are going to be zero. How could that be? Well, what if I had a string tied here? And then what I'd say is the force of gravity plus the normal force plus that tension is going to give me a sum total of forces of zero, so I'm in equilibrium. Once you've identified the direction of acceleration and you can add those forces correctly, it's just a geometry problem, and we can tell by the size of the vectors what the size of the force is.